Hello and welcome to the next of our videos. This will be the start of a very important section. These essential skills videos are designed to help you prepare for the paper one, the physics paper, as part of your matric, but also to understand physics better generally. I'm Dr. Derek Fish. I'm Director of Unizulu Science Centre at the University of Zululand. This video is part 6.1, an introduction to equations. And then we're going to spend quite a lot of time after that looking at specific equations. This is found on pages 37 to 41 in your booklet. Now, when we looked at the photoelectric effect, we mentioned Albert Einstein, who was voted by Time magazine as the person of the 20th century. He published 3 amazing papers in 1905, which changed the world on Brownian motion, special relativity, and the photoelectric effect, for which he won the Nobel Prize in Physics 16 years later. He had something very interesting to say about equations. He says one has to divide one's time between politics and our equations, but equations are much more important to me because politics is for the present, while an equation is for eternity. And that is so true. Politicians come and go, but an equation which is true continues to govern the world. For example, I'm sure you learned in primary school that the area of a circle is pi_r², where r is the radius. But that is not just the area of this circle. In fact, that is the area of any circle. And that is the power of an equation. It solves the problem of the area of a circle for all time and all circles. Here are some of the physics equations which really changed the world. You'll be familiar with Coulomb's law, with Newton's law of universal gravitation. You might have heard about Einstein's relativity theorem, but for the others, I think that you probably will have to continue to physics at university to get hold of them. Now, maybe you tell me you're not interested in some equations you don't understand, which some old guy put together. You would rather just play on your cell phone. Well, let me assure you that without Maxwell's equations for electromagnetism, there would be no cell phones and there would be no cell phone signals. So physics equations do change the world and bring in new inventions and new innovations. So before we get to the start of the equation section, let's just see where equations fit in to the syllabus and the exams as a whole. Let's go back to page 3, which is your contents page at the start of your book. Remember, in my bottom right-hand corner, you can see the page which we are busy on, which will be in the top right-hand corner of your booklet. Now, this is a condensed contents page, and we've now gone all the way down to the skill of equations. But in fact, I need to expand that because we're going to spend most of the series on equations. This next one, 6.1, will be on solving equations. I'm going to introduce you to my progress method. We'll take some time to look at the data sheets, variables, and constants, and then look at an example of using the progress method. We're then going to take this method and apply it to specific examples and specific exam questions. And there'll be one video for each of these because each of these areas of physics has a different equation which needs to be looked at in a different way. Once again, a comment from the examiner. From the National Exam Report, learners still cannot work with scientific equations and formulae. It's very often on the mathematical level that learners are failing. So let's make sure that that doesn't apply to you. Now, where do equations fit into the curriculum? Well, all I can say is everywhere. Mechanics is full of equations. Waves is full of equations. Electricity and magnetism is full of equations. And matter and materials, the photoelectric effect is based on an equation. Don't forget your grade 10 and 11 work. Coulomb's law, that equation came from grade 11. Newton's law of universal gravitation. So please, again, the examiner's comment that grade 10 and 11 work is poorly understood. That shouldn't be the case. Again, looking at the breakdown of your exam, your equations will probably come towards the higher end of the questions. In other words, a recall question will not require an equation, but where you have to analyze, apply, create, and evaluate, these are probably the higher level questions that will require equations to solve them. Now, we've looked at this before, the weighting of different sections in the paper, And I want to tell you, equations will come up in each of those sections. They'll come up in every one of the questions. You have 20 marks for multiple choice. And then the long questions together, the 9 long questions count for 130 marks. Now, let's consider how much of that concerns solving equations. So what I've done is I've taken the exam questions for the last 3 years and compared them. And with the November 2020 question, I've looked specifically at how many of the marks actually concern solving equations. Now, in question 2, the Newton's law question in November 2020, 5 marks out of 16, very few in fact, concerned solving equations. In question 3.2, it was 11 marks out of 15. In question 4, it was question 4.2, which was the majority, 8 marks out of 10. Question 5, there were 3 questions which involved equations, 12 marks out of 14. Question 6, the Doppler effect, 8 marks out of 11. Question 7, electrostatics, 14 out of 17. You can see in almost every case, it's the majority of the marks. Question 8, electric circuits, 10 out of 18 marks. Question 9, electrodynamics, 8 out of 16 marks, a bit less. Question 10, the photoelectric effect, 7 out of 13 marks. Now, adding all that together, long questions count 130 marks, and we find that equations accounted for 83 out of 130 marks. That's 64% of your long questions. And other types of questions, explanations, recall, drawings, graphs, and so on, accounted for the other 36%. Now that is 83 marks is an enormous amount of your exam. And I think it just shows how important equations are and how important it is to get thoroughly on top of your. Now on page 5, what sort of skills do you require for equations questions? Well, just about all of them. And because equations cuts across every question and every section of physics, you will require all of these skills. Under the practical investigation skills, the first one talks about the equation as a form of data presentation. Once again, a comment from the examiner. A severe lack of skills is evident when marking student scripts, mathematical, conceptual, and equations. So once again, let's make sure that that comment will not apply to you. On page 6, we talked about different types of graphs from mathematics. And what's important is that any graph is generated by an equation. And we're going to focus now on the equations rather than the graphs themselves. The equations contain 2 variables and 2 constants. And it's important to remember which are the variables, y and x, and which are the constants, m and c. But now we're going to be focusing more on the equations than on the graph. So in this section, an introduction to equations, we want to help you to develop a strategy which can be applied to any equation in any question. It's no good just rote learning answers to particular exam questions. I would rather prepare you for the type of questions that will come than the actual questions themselves. Now, just before we continue, I want to stress the fact that the focus of this is not just getting the right answer to some exam questions. It's really important that you know how to get there. And we want to look at strategy for solving the equations. For example, I mentioned just now that question 4, the momentum question in last year's exam, 8 out of 10 marks came from solving equations, 4.2.1 and 4.2.2. Now, I want to show you again why I want to teach you skills and not just show you the correct answer. I want to show you the marking memorandum, the script used by the markers for 4.2.2. And what you will see is there's option 1, there's option 2, and there's option 3. And the marks are distributed in different ways. So there's not only one way to solve an equation. And so even if I could just show you, I wouldn't know which way. It's more important to learn the strategies than to just try to memorize the correct answer. The problems will change every year. The strategy you use can be the same. Now, I know sometimes when you see a physics problem, you might really panic. You write out all the equations and facts, draw a diagram, solve it, and get the wrong answer. So you check your calculations and get a new wrong answer. Redo your calculations, get a third wrong answer. Special pleading, check for errors, find nothing. Maybe you start praying. Finally, you locate your algebra error, but you get a fourth wrong answer. You look carefully and find 17 more algebra errors. And finally, you get the right answer and you feel very intelligent for spending 4 hours on a single maths problem until you realize that the problem has 6 more parts, so you become a poet. Well, that's just a funny way of looking at things. If this is how you feel when you see a physics problem, I really want to help you, and it's important to have a strategy. If you find when you look at the problems you don't know where to start, then I can definitely help you. And even if you never finish the problem, you can get lots of part marks just by knowing where to start. Remember, if the question is for 6 to 8 marks, the final answer will only be worth 1 of those marks. So I want to introduce to you a method I put together called Progress. It's an acronym, so each letter stands for a word, and that will help you to remember the method in the exam. So the first P of Progress stands for picture. Draw a picture if it helps. Don't make it a work of art. Don't get out your crayons and color it in. Just draw a simple sketch that might help to solve the problem. Secondly, R for required. Check carefully what is required. In other words, what is the question asking? Thirdly, O is for obvious. Look out for something that's obvious. For example, if they're talking about free fall, then you know acceleration is equal to g. Then look at what is given. So look at what information is given. And then R, relate what is given to what is required by E, choosing the correct equation. Now you're going to find that from your data sheets, and we'll spend some time looking at those data sheets. S is for substitute. Substitute values into the equation. Leave out the units for now. Just put the numbers in. And then finally, S, solve the equation. But of course, your final answer must have units. So lower down on page 37, a bit more information about this progress method and also relating it to the CAP skills, which you learnt on page 5. So let's have a look at these. First of all, drawing a picture. It might be a vector diagram, a free body diagram. It might be a momentum picture. You don't always need to draw a picture, but particularly where there's motion and directional motion, it can be helpful. For this, you'll need to know skill number 1, your models in science. Secondly, looking at what is required. Sometimes it's not obvious. If the question says, when did this happen? Then they want you to calculate t for time. If it says where, they want you to calculate delta x, the distance. Check what is obvious. So for example, from rest means initial velocity equals 0. Make sure you use the correct constants. So skill number 9, constants in equations, is a very important skill that we'll look at as well. Proceeding, G is for given. Identify your values, make sure your units are correct, and make sure you understand the SI system. So skill number 2, scientific notation, very important to be able to handle that properly, including how to put the numbers into your calculator. R is for relate, and relate, you need to relate what is given to what is required with an equation, and you'll probably have to change the subject of the formula. That's skill number 4. So for example, if you have Ohm's law V equals IR, but you need I, you need to be able to change the subject correctly. So the equation is what you need. You must study the data sheets, and we'll give you an exercise just over the page to help you know your way around your data sheets better. Also fractions and ratios, skill number 6 is important. Then the 2 S's, substitute. And sometimes you might need some basic trigonometry skills for that. Only the values, but make sure the units are correct. Just don't put the units in. It gets cluttered. And finally, solve. And when you get your final answer, make sure you have the units. You might need skill number 3, conversion of units, and make sure that you give the direction if it's a vector quantity. Fortunately, when solving equations, you don't need to learn the equations by heart. They are given to you in your data sheets, but I've already stressed just how important it is to know your data sheets well. So let's take a look at them now on pages 38, 39, and 40. These data sheets will be given to you in your exam, and they're a real gift if you know how to use them well. They're very carefully organized. What I've got here in the blue lettering will not be on your data sheets, so you might want to fill it in your booklet on page 38. The first four equations you have are the equations of motion, and they will come up most commonly in question 3 on projectile motion, although they could conceivably be needed for some other questions as well. Below those, we have the force equations, which come up in question 2 on Newton's laws and question 4 on momentum. Lower down on page 38, we have the work, energy, and power equations that come up particularly in question 5. And then at the bottom of the page, wave, sound, and light come up in question 6, the Doppler effect, and question 10, the photoelectric effect. Although something like the wave equation or period is 1 over frequency would probably be needed for both. Turning to page 39, we have the electricity equations. First of all, electrostatics for question 7, Coulomb's law and electric fields. Make sure you know which is which and when to use the different forms of the electric field law. Under that, for question 8, we have all the circuits laws, and at the top right, internal resistance, and at the bottom, the work and power equations. Some of these, like adding resistors in series and parallel, go back to grade 10. Make sure that you haven't forgotten them. And at the bottom of page 39, electrodynamics and alternating current. Your root mean square voltage and current, and how to calculate average power. Now, equally important are your constants on page 40. And again, these are given to you. You should not be searching through these. You should know exactly when to use each one. Probably the most common one is G, the acceleration of gravity, which could come up in questions 2, 3, 4, 5, and 7. The universal gravitational constant will really only be used in question 2, along with the radius of the Earth and the mass of the Earth, if you're asked to do a space-related calculation. Then speed of light in a vacuum and Planck's constant will be part of the photoelectric effect in question 10. Coulomb's constant K for the electrostatics, question 7, and charge and the mass on the electron could come up in question 7 or 8, or possibly even question 10. Now, these numbers all look quite similar, but I can assure you they're very different, depending on whether they have a positive exponent, a large number like the mass of the Earth, or a negative exponent, a small number like Planck's constant. So I've actually written these numbers out for you, and you can see why we use scientific notation, because it would be very difficult to keep track of all the zeros. You can see the mass of the Earth is a very large number of kilograms, but Planck's constant is an incredibly small number, as is the mass on the electron. So please make sure you can handle exponents and that you know how to use your calculator correctly for this. These formula sheets will be no good to you if you don't know what the symbols stand for. Now, for example, if I asked you what V stands for, you could say velocity or volume, and you would be correct in both cases. So it's important to know when is it being used for one and when is it being used for the other. So we've given you an exercise at the bottom of page 40, and we encourage you to go through this. Make a table like this with heading symbol, quantity, and unit. Write down all the symbols from all the equations on the data sheet, and then see if you can fill in the quantity, not just velocity, but initial velocity, and see if you can fill in the unit in words and in its abbreviated form. If you can do this for everything, it will really help you to get your head around the data sheets and the constants. So be grateful for these data sheets. When I did physics at university, we were allowed to write anything we wanted on a single sheet of paper, but it kind of looked something like this. It was very chaotic, and I'm not sure quite how helpful it was. Your data sheets will be very helpful to you as long as you know your way around them. So it's really important to be thoroughly on top of your data sheets and lists of constants and know how to use which equations where if you're going to be able to do well in equation solving. So having gone through this progress method and having considered the data sheets carefully, the progress method will only make sense if you use it in practice. So let's proceed to do that. On page 41, there's an exam question there. Even though the answer is given on page 41, I want to encourage you to pause or stop the video here for 5 minutes. Just look at the question and try to complete this yourself. Just a 5-mark question, you can see there, so it should take 5 minutes. Try to use the progress method on page 37 to answer this for yourself before you continue. So let's have a look at this question from the photoelectric effect. You've got blue light from a light bulb shining onto a metal plate, and electrons are released because obviously the blue light is above the threshold frequency of that particular metal. So the work function has been overcome. The wavelength of the blue light is 470 times 10 to the minus 9 meters. Please notice it's usually the frequency you want, but the examiner often gives it in terms of the wavelength. We're told the bulb is rated at 60 milliwatts. Now remember, 60 milliwatts means 60 times 10 to the minus 3 watts. And a watt is just a joule per second. But the bulb is only 5% efficient. So we can calculate quickly 60 times 5 over 100. Actually, it's only 3 milliwatts of efficient energy from the bulb which strikes the metal. Question says calculate the number of photons that will hit the metal plate per second, assuming that all the light from the bulb hits the metal plate. So it's not immediately clear how to start. So in order to make progress, let's start with progress. So picture is given. In this case, I don't really think a picture is necessary, but if it helps you, that's fine. What is required is the number of photons per second, which we can call n. But you're not easily going to find an equation for n. What is obvious as a constant is the speed of light, c, and of course Planck's constant is also given to you. What is given to us? You're given the bulb power, and we've already done a little calculation to say 60 milliwatts at 5% is 3 milliwatts. We've just multiplied 60 by 5 over 100. And we were also told that the blue light has a wavelength of 470 nanometers, or 470 times 10 to the minus 9 meters. Now we need to find n, the number of photons, in terms of the wavelength and the bulb power. So basically we're going to calculate how much energy from the light falls on the metal in 1 second. Then we're going to calculate how much energy there is in each photon of blue light, and by dividing one by the other, that will give us the number of photons per second. As always, we go to our data sheets to find the equation we need. We're on page 38 if you want to look there. This is question 10, the photoelectric effect. So we'll be looking down at this area. And in this case, we need E equals HC over lambda. E equals HF is no good because we don't know the frequency of the light, but we do know the wavelength. So that is the equation we take back and put into our equation section here. Now to substitute in the energy of 1 photon of blue light equals HC, those are just constants. H, Planck's constant, 6.63 times 10 to the minus 34, and C, the speed of light, 3 times 10 to the 8. Those come straight from your constants page on your data sheets. We divide by the wavelength of the light, and we'd already made a note of that as one of the things given to us. And that gives us the energy of 1 photon is 4.232 times 10 to the minus 19 joules. So the number of photons per second is going to be the energy of the bulb per second falling on the metal divided by the energy of 1 photon. Now, energy of the bulb per second, we've already said was 3 milliwatts. And of course, that just means 3 times 10 to the minus 3 joules per second, because a watt is a joule per second. We divide by the energy of 1 photon, and that gives us an answer of 7.09 times 10 to the power of 15 photons of blue light. Now, again, that's a very big number, but of course, there are always millions and millions and millions of photons. So we think that's a reasonable answer. The question was worth 5 marks. How are these 5 marks allocated? 1 mark always for getting the correct equation from the data sheet. You can always get 1 mark just by knowing your data sheets. 2nd mark for substituting in correctly. The 3rd mark for that calculation, that the effective bulb power is 3 times 10 to the minus 3 joules per second. The 4th mark for doing that final substitution correctly, and the 5th mark for getting the correct answer. Once again, even if you made a mistake right at the end, you can still get 4 out of 5 marks. So that brings us to the end of the short introductory section on solving equations. We've covered the 3 areas highlighted in yellow here. What will follow is specific videos dealing with specific equations for specific subject areas. Let's heed the examiner's warning that learners still struggle to work with scientific equations or formulae. And remember what Albert Einstein said, politics is for the present, but an equation is for eternity. The other thing which is for eternity is your matric certificate. Work hard and make sure that it's as good as it can be, so that you'll always be proud of it, and it'll always help your progress and not hinder your progress. Don't forget to stay connected and watch an inspiring interview at the end of this video. So it's my great pleasure to have a chance to talk to Professor Aswindini Muronga. He's the Executive Dean of the Faculty of Science at Nelson Mandela University, which has campuses in Port Elizabeth and in George. Welcome, Professor Muronga, and thank you for being with us. Why don't you just tell us a little bit about how you got into science? Where did you start? Where were you born and your schooling?
Thank you very much, Derek. I'm currently based in Port Elizabeth at Nelson Mandela University. I was born and raised in Ramondo villages in Wembe district of Limpopo province here in South Africa. I started my schooling in the villages of Ramondo, and that's where I completed my primary and my junior secondary school. I then studied for 2 years, grade 11 and grade 12 at Mbilwi Senior Secondary School in Sbasa in Wembe. After that, I went to the University of Venda where I did my BSc in mathematics and physics. From there, I continued to the University of Cape Town where I did my BSc honors in theoretical physics, as well as my master's in science, again in theoretical physics. After that, I went to the USA, United States of America, to do my PhD in theoretical physics. After completing my PhD in theoretical physics, I went to Germany to pursue my postdoctoral studies at the University of Frankfurt, and also a postdoctoral fellow at GSI in Darmstadt, again in Germany, before I returned back to South Africa, where I was employed and appointed as a senior lecturer in the physics department at the University of Cape Town. And I spent 5 years there before I moved to Johannesburg, where I was the director of the Soweto Science Centre at the University of Johannesburg, as well as an associate professor there in the physics department. I spent 5 years there before I moved down here in Port Elizabeth, where I became the Executive Dean of Faculty of Science in 2016, a position that I still held up to now.
Thank you. So I'm glad to see we've got quite a lot in common. We both did honours in physics at UCT, and we've both been directors of science centres. So that's fantastic.
Yes.
It's really encouraging to see how from humble beginnings in Limpopo province, physics has literally taken you all over the world. Prof. Moronga, you've also been involved in the Institute of Physics. Tell us about that.
Yes, I've been a member of the South African Institute of Physics for a long time. And in 2015, I became its president for 2015 to 2017. And after that, 2017 to 2019, its immediate past president. And currently, I'm the ambassador of the Teachers Development Project within the South African Institute of Physics. I'm also involved through the South African Institute of Physics with other physics projects in the Council of the African Physical Society in the continent. I also serve in the International Union of Pure and Applied Physics, representing South Africa.
That's fantastic, and that's a wonderful track record. Obviously, you don't need convincing that physics is important, and neither do I. But for the students who are watching this, can you tell them why you think physics is such an important science?
Yes, physics is very important science because it is needed in almost in everyday life. Whatever we see around us, the how and the why of the things that we see around us, you need physics to understand. You need physics to understand why the sky is blue. You need physics to understand why we have got X-rays in hospitals. You need physics also to understand even the financial markets. You need physics to understand why we have got seasons, for example. So everything you look around you, even as we speak now through this Zoom video conferencing, it's based on physics principles. So almost everything, that's how important physics is. And in all the sciences, physics is the basis and it's fundamental in understanding also the other sciences. So it's very, very important for students to pursue physics and to excel in physics itself. Therefore, this paper one is very important, which is the physics. I can relate a story, Derek, that if you do well in physics, by the way, you will do well in other subjects. We have got statistics that prove that. We have got the best students who were the best in physics Olympiad. They became the top achievers in the country just because of one particular subject, because they worked hard in physics. The other subjects, they became very simple. And let me also say that you need mathematics to be able to do those problems in physics. Therefore, make sure that your mathematics really is top notch. Because with mathematics, therefore, you just need to understand the concepts of physics.
Thank you so much, Professor Moronga from Nelson Mandela University.